Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about the concept of kinetic energy and energy in general, but especially kinetic energy. So in my previous video I introduced the concept of work. So you may recall that work is given by force dotted with displacement. You may recall that I introduced that this had units of joules, J, that a joule was equivalent to a Newton for a distance of 1 meter. And in today's video, what we want to do is consider energy. So in some sense, the energy of a state is the amount of work that that state could potentially do or could do. Or put differently, it's the amount of work that might be done to bring that state into to that level of energy. So energy can be converted to work, or vice versa. And essentially, that means that energy has the same units as work. And that's true whether we're talking about kinetic energy or some other type of energy. So we could say it also has units of joules. Now, when you do work on a system, what you basically are doing is changing the energy of that system. And there's a theorem called the work and kinetic energy theorem, which typically is how this plays out. We could say work is equal to delta K, where K represents kinetic energy. However, as we will see in future lectures, it's possible to do work against a system, against some other force in the system, and store that as potential energy. So in some sense, what this really should say is that the net amount of work, or the total amount of work done on a system, should be the change in kinetic energy of that system. So now we ask, how is kinetic energy defined? Well, one way of doing that, and this kind of brings us back into another level of recall. So recall that sum of forces, which represents net force, is equal to mass times acceleration for our system. And recall further that 2 times A times delta x is equal to V final squared minus V initial squared. So from these statements, given a constant value of net force, given a constant mass of the system, if I multiply everything by m, I could say 2 ma delta x is equal to V final, and these really are V final and V initial x's for what it's worth. We end up like this. And so this right here is F net. This is delta x. Let's reduce the motion into a one-dimensional motion, so we don't need to include the x's in the subscripts here. What this ends up giving me is, if I divide both sides by 2, so over 2, over 2, and over 2, is that, and I multiply both sides by mass, so I have an m over here and an m over here, is that the work is equal to 1/2 mv final squared minus 1/2 mv initial squared. Okay, so from that, we can define what we would call kinetic energy. So kinetic energy. And this is basically energy of motion. And so at this point, we would just simply say kinetic energy is given by 1/2 times the mass times the speed squared of the thing which is moving. In fairness, this is not the fullness of kinetic energy. This is what's called translational kinetic energy. And translational kinetic energy can be distinct from rotational. So as distinct from rotational kinetic energy. Rotational kinetic energy basically is still energy of motion, but it's energy of motion because a thing is spinning or rotating or revolving. And we will kind of look at this one, rotational kinetic energy, we'll look at in a future video. So in a future lecture or video. We are focused on this one right here, translational kinetic energy for now. Okay, so what is the translational kinetic energy? It's half of the mass times the speed squared. And that's basically all there is to translational kinetic energy for an object. It is a scalar term, so this is scalar. This is a scalar. All energy tends to be a scalar. So all energy is scalar, just like work was scalar. And there's really kind of two things, I guess, that we could do from here. One is we could compute a kinetic energy from something like the speed of an object and its mass, or, given two of those three things, compute the other. The other thing is that we could use the work in kinetic energy to calculate what is the change in kinetic energy for an object. So let's look at some examples. For our first example, we have a 2 kilogram rock traveling at a speed of 12 meters per second through the air, and we just want to determine its kinetic energy. So the kinetic energy should be 1/2 mass times speed squared. That's 1/2 times 2.0 kilograms times 12 meters per second squared. And that comes to 144 joules. So that's it. The kinetic energy is about 144 joules. I've kept more significant figures than is allowed, but I don't want to be too pedantic with that. It would be 140 if we round to 2 sig figs. Example number 2, we have a 5 kilogram block and it's sliding along the flat ground at a speed of 4 meters per second. We want to know how much work friction does to bring it to a stop. We're kind of neglecting air resistance here. So work should be equal to change in kinetic energy. So that is 1/2 mv final squared minus 1/2 mv initial squared. Finally, it is stopped. So stopped means that this first one goes to 0. So work becomes 1/2 times the mass, 5.0 kilograms, times the speed, 4.0 meters per second, quantity squared. Work is negative because the thing is slowing down. So work becomes 20 joules. And that's how much work is done in bringing it to a stop. Okay, a conceptual question. Which of these has the greatest kinetic energy? An object of mass m and speed v, an object of twice as much mass but half as much speed, an object of half of as much mass and twice as much speed, or do they all have the same value? So in this case, k would equal 1/2 times m times v squared. In this case, k would equal 1/2 times 2m times 1/2 v squared. 1/2 of v quantity squared. Okay, that's 1/4 times 2, which is a half, so you end up with 1/4 mv squared. This one right here would have k equals 1/2 times another half m times 2v squared. Okay, so the 2 squared gives me 4 times 1/4. This ends up with being equal to mv squared. So they are not all the same. This one right here has the greatest value of kinetic energy because it's mv squared as opposed to half mv squared or 1/4 mv squared. That's about it for today's video. We've covered kinetic energy, we've covered the work in kinetic energy theorem, we've done a couple quick calculations, and that's all that I was planning to do. So hopefully you learned something from watching this video. I know it's a little bit more simple than some of my other videos. Hopefully that's a nice change of pace for some of you. And thanks for watching, and see you in the next one.